The city of Sydney has come a long way since its beginnings in 1788. There are nearly 2.5 million people here now, and all around them are the signs of continuous lusty growth. But there can be no growth without power, the power that electricity provides for industry, for transport, education and research, and for the everyday domestic needs of heating, lighting, cooking, and countless thousands of household appliances. So electricity supply authorities are continually planning to meet the demands of the future. Always they must think in terms of more and bigger power installations. Sydney's nightlife means entertainment and relaxation for thousands of visitors, but behind the bright lights there's still a tremendous call on the city's power supply. Many industries work through what used to be called the hours of darkness. There's no let-up for transport, hospitals, the newspapers, radio, television. How many traffic lights are there in Sydney? How many advertising signs? When the New South Wales Electricity Commission planned its Liddell power station, the installation called for 4 generators, each of 500 megawatts. To cool each generator set required 215,000 imperial gallons of water per minute against a varying head of 27 to 45 feet. For this job, Thompsons undertook to design and build 5 108-inch mixed-flow pumps, the biggest of their type in the world. Each pump was to be driven by a 3,900 horsepower English Electric Company motor through a gearbox at the speed of 214 revolutions per minute. One pump was required for each generating set, with the 5th a standby unit. To ensure maximum power from the station, it was essential that power used by the auxiliaries, including the pumps, be kept to a minimum. The normal characteristics of a mixed-flow pump are shown by the head flow and power curves. For a specific duty, the pumping system has a definite resistance, governed by pipe size, length of pipe, and static head required. Every system has an inherent resistance. Under actual operating conditions, the system resistance is usually less than the estimated value due to the use of conservative friction factors. Consequently, the actual flow output of the pump under duty conditions is greater than the design flow. By the introduction of pre-whirl to the water entering the impeller eye, the head flow characteristic of the pumps can be reduced, so that the actual output corresponds with the average required flow of the system. This pre-whirl is obtained by the use of a set of variable pre-stator blades, which are located in front of the impeller. This method of varying the head flow characteristic has been found to have the least effect on pump efficiency, resulting in an overall power saving. The pre-stator blades can impart a maximum of 75 degrees pre-whirl with corresponding reduction of the head flow characteristic. This reduction is effective in reducing the horsepower absorbed by the pump at startup. The requirements of the Liddell station were such that each pump had to be suitable for variable duty. After considerable research, Thompson's designers decided upon a fixed speed pump with head flow variation to be obtained by means of adjustable pre-whirl blades on the inlet side of the impeller. Technical calculations were accomplished as speedily as possible by the use of desk-type computers. The final stage of work in the computer room came with the interpretation of the figures and their application to the job. Before going ahead with the manufacture of the 5 108-inch pumps, a 24-inch model was made and submitted to an exhaustive program of tests. The model was set up to operate under conditions exactly equivalent to those at the site of the full-scale pumps at Liddell, and these conditions were maintained until, on the completion of testing, the behavior of the pump had been observed under all possible operating conditions. One important feature in which the test pump differed from the full-size design was the provision of a transparent casing. This enabled the use of a strobe light to make a close study of the cavitation limits of the impeller blades. Thorough testing like this has been a feature of the research work carried out at Thompson's for many years. As long ago as 1939, a hydraulics laboratory was installed to help in the development of pumps and associated equipment. Continuing investigation using modern methods like these adds still more to the company's knowledge of hydraulics. In this particular project, all tests gave satisfactory results. The 24-inch model pump was accepted as the basis for the design of the big fellows, which would play such a vital part in the successful operation of the Liddell power station. The engineering department then had the task of preparing detailed drawings. Between the completion of drawings and the manufacture of the castings which would make up the complete pumps came the work of the pattern makers. In the pattern shop, the engineer's work, so far expressed only on the flat surface of the drawing board, took solid three-dimensional form in timber. Pattern making is a craft in itself, and each completed wooden pattern represents a substantial investment in time and money. Being assembled here are the patterns for the tapered liner of the 108-inch pump. Patterns were also necessary for the impeller blades, pre-stator blades, diffuser blades, and other parts. All patterns are made to the highest possible degree of precision. This was particularly so with the 3 sets of blades. Accuracy was essential, and precise allowances had to be made for the contraction which would take place when the blades were finally cast in stainless steel or spheroidal graphite cast iron. The finished patterns were used to make the molds into which the molten metal was poured to provide the castings. Foundry work is always spectacular, and there's no place for inefficiency. After heating, the specified metal is run into a ladle, which is transported to the mold by means of an overhead crane. Work in the foundry reached its climax with the actual pouring of the molten metal. Each of the discharge bend castings for the Liddell power station pumps weighed 32 tons before fettling, and this called for a big team of men working together during the pouring operation. After fettling and later machining, each discharge bend was reduced in weight from 32 tons to 26.5. Even in a pump of this size, some components are quite small, but large or small, each part must be machined to its finished dimensions. Here, work is being done on one of the column liners. When the pump is assembled, this liner fits on top of the diffuser. Because of the horsepower absorbed by the pump and the bearing span, a large diameter shaft was necessary. But the weight and cost of such a shaft in stainless steel demanded an alternative that would provide a lighter and less expensive shaft, which would still be just as efficient and durable. It was decided that the shaft should be hollow, made from stainless steel plate rolled to size, with a stub shaft welded to each end. The completed shaft would be machined and balanced. This is how the machining was carried out. Machining of the pump discharge bend presented no problems, thanks to the vertical boring machine built and installed by Thompsons in 1968. Designed particularly for jobs like this, the machine can handle work up to 10 feet in height, 30 tons in weight, and with a diameter of 26 feet. In making smaller pumps, the usual practice is to manufacture the impeller as a unit. That is, the hub and the blades are cast in one piece. However, the large size of the impeller for this pump made it necessary to mount individual stainless steel blades on an austenitic cast iron hub. Each blade is located by a spigot fitting into a matching recess in the hub. When the 9 blades have been set at the correct angle, they're locked in position. The shape of the impeller blades is vitally important, and it's essential for all the blades to be identical. Multiple templates were used to ensure that the blades conformed to the design dimensions. A minimum amount of metal was left on the castings to allow for the final grinding and handwork. The hub of the impeller was also machined wherever possible. This was not only to give a smooth surface, but also to help in balancing the completed impeller assembly. Final balancing of the hub was carefully carried out. Metal was removed where necessary, and where additional weight was required, this was first added in the form of clay. To complete the balancing process, metal weights equivalent to the clay were bolted into position. The stainless steel casing liner was finished to the same high degree of accuracy as all other work in the machine shop. With all the impeller blades mounted on the hub, the outside diameter of the blades was machined to the final design size. Constructing an impeller in this way means a saving in cost compared with unit construction and has other advantages too. The individual components are smaller. If there should be a casting flaw in one blade, the whole impeller is not affected. And if the blade should be damaged in operation, perhaps by a log of wood passing through the pump, only that blade need be replaced. As the assembly of the finished parts begins, the size of the complete unit becomes apparent. Here, the pump column is lowered onto the stool, an operation that calls for precise handling of a weighty item. With the column secure on the stator casing, the column liner is added. The pump column and liner do more than retain the water. They're also designed to control the rate of expansion of the water leaving the pumping element. Each of the 5 pumps was completely assembled before leaving Thompson's to ensure that they would go together at the site without a hitch. Each unit was subsequently partly dismantled to facilitate dispatch. The piece-by-piece assembly of the pump began with the column in the horizontal position. The tapered liner was then added. The assembly could not be hurried because of the size of the individual items. However, no difficulties were encountered, convincing proof of the accuracy attained in making each component. Thompson's is a company completely familiar with the manufacture of centrifugal pumps, large and small, and has pumping installations all over Australia. In 1975, the company will have been in operation for 100 years. Fitting of the discharge bend, weighing 26.5 tons in its finished form, was accomplished without any problems. Just another heavy job to be carried out with a very light and precise touch. The shaft, although built up and not solid stainless steel, still constituted a pretty weighty item. But like all the other parts, it went into place without any problems. Here the collar is fitted to the infuser, which forms the base of the whole unit. The pre-stator blades, which control the rate of flow through the pump, were fitted with the same high degree of accuracy and precision as the impeller blades. Identical blades were mounted in such a way that they moved together and at the same rate. At any time, all are at precisely the same angle. Pumps of this type are rare, not only in Australia but worldwide. This film is probably the only record in the world of the manufacture of such a unit. Before fitting the working end of the pump, the previously assembled parts were carefully loaded onto the railway truck, which later would transport the pump to the site where it was to be installed. In this position, the impeller was fitted into place. The pre-stator assembly, the last of the main components, completed this part of the loading operation. The cone-shaped infuser was designed to take the entire weight of the pump. The lower end is spherical and rests in a mating section mounted on the bottom of the pump well. The gearbox is housed in the motor stool, so it cannot be seen when the pump is completely assembled. Designed and supplied by the English firm W.H. Allen, Sons and Company of Pershore, Worcestershire, the gearbox is an epicyclic speed reduction planetary unit. With a motor speed of 994 revolutions per minute, it drives the pump at 214 RPM. The auxiliary service piping is a vital part of the completed installation. Before dispatch, it was assembled and thoroughly tested. The main control cubicle for the hydraulic operation of the pre-stator blades is itself a miniature pumping station with pumps, motors, pipes and electrical installations. This paint job is the first of many that will be carried out through the working life of the equipment as protection against the effects of the elements, sun, rain and condensation. The size of the complete pump made it necessary for the major components to be transported separately and finally assembled at the site. This is how the gearbox and motor stool assembly was sent on its way. Each part of each pump was thoroughly checked before receiving final approval to begin the long rail journey from Castlemaine. After leaving Thompson's plant, the pumps faced a journey of 800 miles through Melbourne and Sydney and farther north to the site of the Liddell power station near Muswellbrook. Construction of the new power station was already well advanced when the first of the pumps completed its journey. The pumping units would occupy only a small part of the whole plant, but with their task of cooling the big generator sets would be as important as any link in the chain of power production. After unloading, the pumps were prepared for installation. This part of the plant is known as the pump apron. Just as the job was about to begin, nature decided to show that it could provide water in great quantities. It was a spectacular display, but caused only a short interruption to the work on hand. It wasn't long before the pump, which had previously been set up on trunnions, could be raised to the vertical position by the big 100-ton gantry crane. The crane has been provided especially for servicing the pumps and other equipment in the area. It handled its first big assignment without any difficulty. After the pump had reached the vertical, the pivot blocks were removed and the gantry began to travel slowly over the apron, taking the pump to what was to be its permanent location. Before being lowered into the well, the pump was turned by manpower to bring the discharge flange into the correct position. The actual lowering operation had to be tackled slowly and carefully. Each of the 5 pumps received the same firm but gentle treatment. During the final stages of lowering, the flange was cleaned in readiness for connection to the discharge pipe. Now all that remained was the lining up of the holes through which bolts would pass to secure the pump in place. The heavy part of the installation was now complete, but there was more work to follow, even more exacting and time-consuming. The control cubicle was next to be fitted, and then the motor connected to the pump. Pipework, valves, and electrical equipment followed. Final tests were made on each pump before it was pronounced ready for service. With the completion of the Liddell power station, New South Wales had taken a big step towards meeting its future demands for electricity. So many years of service to the people of another state begin for the 5 pumps designed and manufactured by one of Victoria's oldest engineering firms, Thompsons Castlemaine Limited.